Now let's get a bit more formal. Protocols, layers, standards. Oh, this may sound a bit boring, but we need this. Why? Yeah, hold on. So, let's go back. What is it really what we're sending, receiving? In the end, what we want to do is we want to send some data, a file, a video stream, downloading from somewhere, etc. But what is this? We cannot transmit a picture. In the end, we all know digital data. So it's ones and zeros. That's what we can transmit. Digital binary data. Typically, everything is represented as binary data. But still, this is nothing we can transmit because these are ones and zeros. So at a source, we have to translate this into signals. So we have to translate, and we will learn how we do this, etc., our data, our digital data, into a signal. And how the signals look like, this pretty much depends on the cable or wireless or whatever. So we are not able to transmit this signal. It would rather look like this. Doesn't matter. So how we do this, on which layer, in the end, here we don't care. We have our interfaces. We will learn a lot about also this, how this works. And then we have certain lower layers. We also have a closer look on this. And then we transport this in some kind of virtual pipe somehow on the other side. So there's our destination. So what we do in the end is what we call digital data communication. We process and transport digital data between interconnected computers. So if we talk about digital data, well, what is data? Maybe you know or have a rough feeling so what data is, but let's be a bit more precise. The term of data. So let's start with an apple. What is an apple? So how can we represent this? So we can write the word apple, or we can somehow draw it like this. But why apple? Why not? We could also write something like this, manzana, or Apfel, or whatever. So an apple can be represented in many different ways. Okay, so, but in the end, we all think of something. So we think of an apple in our brain. Not only about objects, facts, concepts, ideas, models, whatever. This all happens in our brain. So we know, okay, that's an apple. Great. The point is, we cannot transmit our objects of thought. How should we do this? This is why we have certain conventions of how we represent these objects in our thoughts. So we represent them in a formal way. So what is this data? Data, in the end, is a representation. So you see here, representation of these facts, concepts, models, etc. in a formal way. And now the important part, which is suitable for communication, interpretation, and processing by human beings or technical means. What does it mean? If you read a word like Apfel, and if you're German or you know German, then, well, it's quite clear, it means an apple. So we have a representation that is suitable for communication, interpretation by human beings or by technical means. So if you know the coding, in the human case the language, if you know how you code it, then you can interpret it, process it, etc. So simple examples, the spoken language, sign language, written language, etc. So we know this is an A. Okay, but you have to know this representation. And also important, you have to agree upon the representation, because otherwise you may think, okay, this is a A, but what does this little circle mean on top of it? If you know one of the Nordic languages, Swedish for example, you know what it means. So you have to know this representation. And one very, very, very basic way of this coding, ASCII, American Standard Code for Information Interchange, one of the very first old character encodings. There are many, many, many more, limited to the English characters, Latin alphabet, containing printable, no printable, and control characters. So it starts here. Here we have the printable, so exclamation mark, etc. We have the alphabet starting here, and so on, capital letters, small letters, and it ends, it's a 7-bit alphabet, it ends with the delete. Delete, that means all bits are set, as I said, 7, and if you think it is old systems punching holes, then delete means all the holes are basically punched. So that, by the way, was a way to correct something. So if you're interested in some more details of coding and different alphabets, etc., please do have a look in the internet. So it's all very well documented. Okay, the next term, information. Pretty often mixed with data and information. So it's quite often said, okay, we exchange information, the internet transports information, etc. We will learn that no, we here in this course and also the internet, we talk about data and what is the difference between data and information. So first, let's have a look at some more formal definition. What is information? Whatever is capable of causing a human mind to change its opinion about the current state of the real world. See, if you get information that changes your mind, your opinion, then that's the information. So formally, especially in science engineering, information whatever contributes to a reduction of the uncertainty of the state of a system. Okay, what does it mean? And what's the difference when we talk about data and information? So, what changes your opinion? If you watch the news the first time, we, with the help of the internet, transmit data for the news program. You watch it the first time. Then, this data will contain information for you because this changes your opinion about something. If you watch the identical news the second time, the third time, etc., it contains no information if you paid attention the first time. So, although we transmit data all over again, there is no information contained in the data because in your system there's no uncertainty anymore because you saw the news. So if you watch the same show, the same news several times in a row, there is no information for you in there. But you still, and all the machines and the network, have to process data, transmit data. Here, in this course, we do not really care about information. We care about data. We know there's coding theory, information theory, etc. But in general, we talk about data. So, the point is, information, basically, that's something for humans to handle. Machines and humans can handle also data. We can write something without knowing what it means. Machines don't know what it means and they simply process data. So that's data. But for the classical definition, only humans can handle information. And also please distinguish information from the medium that is capable of carrying it. So that's also a difference. So we talk about networks and computers, etc. We talk about cables, but that's a difference. So the point is that information is typically tightly coupled to humans. we can discuss this. Yeah, AI, what is this science of intelligence, and is this information processing? That's also a term quite often mentioned. So that's something to discuss. But here, to make life simpler, we talk about data. Okay. We cannot directly transmit data nor information because we have the world around us. So it's nice to talk about data, this kind of abstract representation of something. But as soon as I write something, for example, the word apple, or if I draw something, what is it in the end? If I draw this, or if I write apple, well, so there's a variation in the color between white and red. So in the end, this is pixels, different colors. So I code this word or the picture in a different pixel colors. And this means in the end, a change of certain physical parameters. Or if I say word apple, then this is basically different air pressure, and this is interpreted by our ears. So we code the data in a way that our ears can receive it. So here we have our objects. That was the apple, our abstract world. We represent them as data in a formal way, something we can then manipulate, process, transmit. And then we have to convert it in a way that physics, nature can actually transfer it. So we need signals as a real representation of data. So data still is abstract. So this is A, B, C. This is apple. That's abstract. But we need something that really represents it, something that is transferable. So we are not that much concerned about signals in this course. We use them, we briefly touch them. We use basically an interface to a black box, and that's then somehow transmits this. So a signal in the end is a physical representation of data, by spatial, timely variation of certain physical characteristics. So air pressure, for example, or a color, or there are electromagnetic waves, etc. So the idea is that in the end, for us humans, this parameter contains the information, information, yeah? And then we can transfer this information via electronic system. Well, for us, it's okay to transfer data, whatever it then means in the end. So signal, voltages, amplitudes, waveforms. So there's many different things, but in the end, the signal is the real physical representation of this abstract representation of data. Okay, so now we know a bit more about data, information, signals. What else do we need? Well, something that sometimes is boring. Standards. Many people think, oh, standards. Piles of paper, long discussions, very complicated. But we need this. So, for example, if you meet each other at a party as humans, when are you allowed to speak? There are certain conventions, standards. But also at the same time, there are certain conventions for the encoding. So if you meet someone, you start talking English, for example, or German or Spanish or whatever language you like, or you give certain signs. That's also a way of speaking to each other. And the same is true for computers. Think of a setting where we have many computers in a room, all with their antennas, and you have an access point here, several antennas, and then when are you allowed to start sending? Because if you send, for example, at the same time, there's a collision. Doesn't work. In addition, what are you sending? Does the other side understand if I send an A? Maybe not, or maybe. So it depends. So if you send something, just our example, the other side doesn't understand, oops, what happens? So we need certain standards that tell us when we're allowed to speak, how we encode things. Why do we need this? Well, the world is not homogeneous. We have many different networking infrastructures. We learned the internet is a network of networks. So different infrastructures, different computer architectures, they all may, well, have different languages, different encodings. Maybe you remember big endian, little endian, or different alphabets. So there's a Chinese alphabet, the Latin alphabet, Japanese, whatever. So we have different applications that are distributed. So the world is heterogeneous, it's not homogeneous, it's not one company produces all the systems. There were some monopolies in former times where I said, okay, if I buy an IBM computer, everything is IBM and they know what they do, they know the coding, etc., etc., etc. No, we have different computer architectures, different systems, but all the participants should at least be able to talk with each other. So we need certain protocols, certain conventions. But what is a protocol? Well, in the end, a protocol is a convention. It contains certain syntax, certain semantics. So how do I describe it, the syntax? How do I write it down in the end? And semantics, what does it mean? And the classical thing between humans is that, okay, well, Alice says hello and Bob answers with hello, and then, okay, maybe not humans, maybe computers with the names Alice and Bob, give me whatever the homepage of the university, something like this, and then this will be the answer. So you see, these are our time sequence diagrams where the time flows from top to bottom, and you see these arrows going from left to right, from right to left, and they always go a bit downwards because clock is ticking, and so please never draw it like this so the time doesn't go backward. So, okay, so don't do this. So we need some conversations, so rules, syntax, because I have to be able to interpret this hello. But what does it mean, hello? If someone says hello, or hola, or hello, or hey. So what does it mean? And how you really write it. And you all know that in the end, we send data packets. So we have to know what the bits mean in these data packets and how many bits we have for certain purposes. So again, what is a protocol? Rules of interaction between elements of a network, between humans. So we ask, what's the time? I have a question, etc., etc. So we introduce each other, all these things. And here we have machines, rather machines. So for network protocols, we have the machines. And all these activities in the internet are governed by protocols. So we always have rules, huge rule sets or simple rule sets, huge standards or very simple ones, but all the communication activities are governed by these protocols. So, and these protocols, the rules must be specified extremely precisely. So, in general, well, we have to know what the messages mean, and we know what actions we take after we receive a message or another event happens. So you could receive a message like, good morning, and you answer with, good morning, how are you? Or another person approaches you and nothing happens. And after a timeout, some seconds, you may say, hello. So you take the activity on your side. So the protocols that define the formats of the exchanged messages, the order of the messages sent and received, and the actions we take on message transmission and reception. So that's what we have in the protocols. So once more, just to make it clear, we have it between humans, also between machines. We say hi, we get an answer. We ask for the time, we get an answer. That's a classical flow of a conversation of messages between humans. And that's the same for the computers. Connection request, a connection response. You ask for a certain data, file, stream, whatever, and you get it. So very, very simple. It will get more complicated over time. But that's the basic idea of protocols. Okay, once more, a motivation, protocols. Think of where we have the protocols. Think of what's the protocol we use in the World Wide Web. Maybe grid computing, etc. So the important part is it must be unambiguous. It must be quite clear. So a set of these unambiguous specifications, we define how the process communicate. And you see in the example on the right-hand side, well, there might be a problem. A problem you don't understand if you don't know German, because if someone says eagle in English, the other one might think of this little cute animal which is called eagle in German, not in English. So, okay, we also have to speak the same language, etc., to avoid misunderstanding. And this includes a lot. For example, the type of the message, the syntax, semantics, the point in time when we send, when we respond, how we multiplex, how we control, do we have priorities, how do we act upon errors? That's a big, big, big issue, and many more technical details. And one important thing, John Postel, one of the really big guys of the internet, said, please be very conservative in whatever you do and be very liberal in what you accept from others. Well, maybe this is also true for humans, but this is definitely true for the world of protocols. So be conservative what you do, know exactly what you do, don't do strange things, but please be liberal in what you accept. So if there happens an error, don't be shocked, no panic, maybe a simple reset, or maybe try to repeat something, etc. So that's something you should remember. Okay, now if we think of the internet, big, huge, that's quite complex. And now we have certain rules and protocols and everything. How can we handle all this? How can we really master this complexity? And there's something we always do if a system is huge. We have to structure it somehow. And one way of structuring something, it's what the Romans know as divide et impera, divide and conquer. So is we split the system in certain, subsystems. And in the communication world, we like layers. Layers, what does it mean? So we have basically a huge black box. We don't know what's inside the black box, and to be honest, we don't care. Well, we do, because you took the course. But in the end, we have a certain service access point. This is what our sockets are, for example, for internet programming, and we access a service there. That's like if you go to a counter at the bank or whatever, you do not care about the banking system. This is the black box, but you want to get money. So you walk to an ATM, your interface is exactly, you insert the card, etc., and you will get money. And everything else is a black box. It's very complicated inside the black box, but we don't care. That's one way of mastering this complexity, to separate different layers. So if we look inside the box, we see certain layers using, again, black boxes, and so on, and so on, and so on. So that's the idea of layering. And this is exactly where we use protocols. If one layer wants to talk to another layer, or same layer on another machine, then we use a certain protocol. The layer can also talk to lower layers. There we also use certain protocols. We use these service access points. The protocols we're talking about here are the protocol and their elements, messages exchanged virtually between peers, entities of the same layer on different machines. So layer n talks to layer n plus 1 talks to layer n plus 1. Typically, we should never talk across layers. I know this is done for efficiency purposes, etc. But typically, we don't do this. So strict layering means a layer n talks only to layer n. And we exchange data virtually with the help of a protocol. Why virtually? Because real exchange always goes down all the layers and then somewhere over to the other system and then up the layers again. I'll come back to this. So, layering helps us to master the complexity of large systems. And all I see is a service access point to a black box. And then someone sits inside the black box and uses yet another black box or many different black boxes. And that was also the idea in the 80s to organize and to sort out this complex communication network, growing and growing and growing, by the International Organization for Standardization coming up with a layering model. The well-known 7 layers you should know from the basic courses, so starting from the physical layer, data link layer, network transport, session presentation, and application layer. And we also learned in the basic courses that in the internet world, we typically do not have explicit session and presentation layers. We have the ideas of session and presentation layers also there, but we rather focus on applications running directly on top of the transport layer. We have the internet layer, and this is where basically the internet, the IETF, I'll come back to this later, there's all the standards, transport and internet layer, right? Some towards application, etc. And then we have the host to network. This is where we have our wireless LANs and Ethernets, etc. And there, for example, IEEE does a lot. There we also have Bluetooth and some others. So that's one way of structuring this complex system of communication systems. And we had also in the bachelor course a closer look in, well, how does it look like when we have certain applications or, say, a Unix process, for example, accessing here the communication stack using a socket. We'll come back to TCP and IP later. And then we have the protocol stack, and data flows from, let's say, a client, a web browser, across the stack, down into the network. Then we have intermediate system, for example, a router. And then we go to yet another network and coming up on the other side of the server. And then depending on the protocols and the port number, we will offer the data to yet another process. And the core idea of all this networking is that we create a logical connection from one side to the other. That's the idea, to exchange data. But as you can see, that's only logical. It's kind of virtual connection. So we have a TCP connection, for example. In real systems, we all go down through all the network stack, and then coming up again on the other side. We will have a closer look at all the protocols and how it works in some more details. And what you also learned already in bachelor courses is what this means to the data. That, yeah, we start with our user data, for example, a picture we want to transfer. The picture is still there in all this data down to the physical layer where we have our bits, and there we have certain waves, but we add for each layer typically a header, a transport header. This is where we have the so-called ports in there. We have the network header. This is where we have our IP addressing. We have the data link header. This is where we have our MAC addresses. Plus we have a CRC, a checksum at the end. So this creates a lot of overhead, but this is needed. This is the additional information needed, for example, for routing packets, for checking for errors, etc. The only real transfer of data happens in form of physical signals down here. There is no direct way for the higher layers, so application cannot directly transmit anything to another application. That simply doesn't work. Okay, that was really quick on all this layering, but as I said, this is some basic knowledge you should have. So layering, the basic principle, you should know other examples where you know layering, where we do this. Also, we have learned a lot about protocols. What is it? Again, remember, and what is a peer in this context? If you have a protocol, who is the protocol talking to? Then if you think of all the layers, most of the layers only do some kind of a virtual transport of data, and which layer is really transporting something, data, signals, etc. You saw a lot of encapsulation, so adding some headers, sometimes trailers to data. Why do we do this? What are the advantages? What are the disadvantages? And do you know this encapsulation from other systems outside of computer networks? So now let's think of something completely crazy. What would happen, if you had in the internet only data that really contains information? Just think of this. And what do we really do? What is transported over the internet? And also think of a case, what happens if you do not follow rules, protocols, conventions, as human, as a computer system, etc. Yes, I was quite brief on some of the topics, but please go to our bachelor networking course if you're not sure about these basics. There you will get a lot more explanations.